Welcome to Missing the Mark, where we look for meaning in strange places. I'm Christopher.
Hi. Today we're going to be talking about statistics, and by we, I mean myself and Andrew Stratelotes of the Escaping Atheism Project.
Hey, Christopher.
Hey, like me, Andrew has a background in mathematics, but whereas I've only been familiar with frequentist statistics, Andrew has a background in Bayesian statistics, and so I wanted to talk about what Bayesian statistics are, because they're gaining popularity, I think, as being a much more practical, much more useful, much more understandable and intelligible statistics. So we're going to talk about this to see what it is, and we're going to keep this, our goal is to make this accessible to people who don't know statistics, and we're not going to be talking about formulas and math. We're going to be talking about sort of how to understand it, how to understand sort of what statistics are when you hear about them. So hopefully this will be interesting to everybody, because we're aiming this at people who don't have a math background. So an introduction to the topic is, there's a very interesting, I don't know how many of you watch the webcomic or follow the webcomic XKCD, but there is a very interesting XKCD about statistics a while ago, and it's titled, "Did the Sun Just Explode?" It's night, so we're not sure. And there are two people talking with who have a machine, and it's explained, this neutrino detector measures whether the sun has gone nova. Then it rolls 2 dice. If they both come up 6, it lies to us. Otherwise, it tells the truth. So then one of them says, let's try. Detector, has the sun gone nova? Rolls and then says, yes. Then there are two reactions given. One of them is with a frequentist statistician, who says the probability of this result happening by chance is 1 out of 36, which is equal to 0.027. Since that is less than a p-value of 0.05, I conclude that the sun has exploded. The other panel is the Bayesian statistician, who says, bet you $50 it hasn't. So, given that setup, I'm going to start this off with essentially the question, Andrew, of what did the frequentist statistician do wrong here?
Well, at a high level, frequentist statistics are about the limits of long-term sequences. And this is actually a specific one-time event. So in that sense, he's making an error by using the wrong tool for this job, because the number of suns we have isn't an infinite sequence that may or may not go supernova every moment or what have you. So that's sort of the fundamental issue that we start with. There are ways to sort of tweak this so that you end up being able to use it, but it doesn't really match the sort of assumptions that are usually true in statistics when we handle this type of thing.
Yeah, I've joked in previous, I think in a previous video, that statistics, by which I mean frequentist statistics, is the misapplication of probability to the real world, because the assumption simply can never be satisfied, since we never have infinite runs of anything.
Exactly, and sort of looking at it intuitively, we know that the probability of the sun suddenly exploding is very, very, very small, and the probability of getting 2 dice with 6s is 1 out of 36. So just looking at it intuitively, of 1 out of 36, or 1 out of 36 odds versus, let's say, 1 out of a billion odds, what's more likely? It should be 1 out of 36. And this is related to what's sometimes called the base rate fallacy, where people sort of take the statistics of a test and sort of assume that that test is perfect, even though its error rate will be so high that it's not giving you very much more information, right? Sort of intuitively, you would think, well, it's more likely that it rolled 2 6s, but the chances of the sun exploding might have gone up a little bit, and that sort of is the intuition that Bayesian statistics tries to capture, is that if you were betting on this, how would the bet odds change based on new information.
Mm. Okay, so taking that, why would you say the Bayesian statistician gets the correct answer here? That is to say, how is the Bayesian statistician thinking about these statistics so as to get the right answer here?
He's using conditional probability. So what that means is, given that the machine pings the sun exploded, what are the possible conditions that would cause that, and how likely are they, right? So there are two possibilities. One, the sun actually did explode, and two, the two dice both rolled sixes. And Bayesian statistics is about taking those types of understandings of what causes what and assigning probabilities based on how much you believe things, in the same way that a bookie or an odds maker would assign odds to a football game or a racehorse.
Mm. So now Bayesian statistics is named for Bayes' theorem, right? Which is actually specifically about conditional probabilities, isn't it?
Yes, that's correct. And Reverend Thomas Bayes, who was a English priest, apparently a lot of English priests had a lot of spare time and had developed scientific and scholarly hobbies. His thing was actually gambling. Very good English priest, right? So what he wanted to do is determine like the optimal betting strategies. And in games like poker, some information is revealed as you play, right? So in like Texas Hold'em, more and more cards are shown on the table. And based on how many cards are up, you can sort of realize what people might have in their hand and what hand they might have. So what is the probability of this guy having a flush or this guy having nothing, et cetera, based on the fact that there are no cards there, or there's an ace of spades or two aces, et cetera.
Mm. So that's although I can't help but note that once people started doing that, I believe casinos started just putting in so many cards that they're that it becomes to diminish the amount of information you're actually getting about this. Because as I understand it, like in I don't know if you're familiar. I'm not particularly familiar, but in casinos, I've heard they do things like they'll mix a minimum of 5 or 7 decks together, just so that the having seen 1 or 2 cards coming up doesn't tell you much about the probability of the rest, because there's so many more in a 5 times or 7 time deck, or 7 decks mixed together.
Yeah, no, that's right. And oftentimes the Bayesian approach to like casino games will tell you, oh, your best chance of winning is 49%, and you have to make a 50-50 bet. And therefore, you shouldn't be betting, because in the long term, you will lose money, and you will actually even lose it in the short term rather quickly. So,
yeah, it was. Where's that from? The only way to win is not to play at all.
War games.
War games, right? Yes. Yeah. So now, frequentist statistics, which is sort of where statistics started. Well, I mean, probability is about infinite series, and that works fine because you're in what one might loosely call math land, where you can have things like infinite series. And statistics started historically in taking probability and applying it, to events that would happen. I kind of have this feeling. Do you know the history of it? Actuarial tables for like insurance, were those some of the earliest applications of statistics?
Yeah, frequentist statistics. Bayesian statistics, in some sense, is older because it's sort of the method that Laplace and the other early astronomers used. But basically, statistics came into its own with folks like I want to say Kynes, but I know that's not necessarily true. Fisher in like the 1920s. And that's when frequentist statistics became very applicable and were used for things like actuarial tables. It was also associated with sort of the middle of the Industrial Revolution and statistical controls and things like that.
quality controls in industrial processes.
Right, exactly.
And all cases where they're not dealing with infinitely many, obviously, but they're at least dealing with very, very large numbers, whether people you're insuring in actuarial tables, or if you're producing a million widgets running statistics on them, at least you do have very large numbers involved.
Right, exactly.
So still, the mathematician in me can't help but note that 10 million is still, as a finite number, very, very small compared to how big finite numbers can in fact get. But that's the thing about statistics, in the frequentist model that always bugged me, is simply that you cannot possibly satisfy the assumptions of the mathematical theorems you're in fact using. So now, what would you say? Since Bayesian statistics, I mean, it's called Bayesian statistics and it uses statistical formulas, but on the other hand, it does seem to me to be rather different. And I think I asked you one time, if memory serves, that in some sense, Bayesian statistics is quantifying how little you know.
Yeah, and that's the exact right way to look at it, right? Because let's say that I give you a coin, and you know that there are two possible outcomes. It's either heads or tails. But you don't know if this is a magician's coin that will always go heads, or if it's a coin that I got from, the mint, and it will get each head with about the same probability. And that's the uncertainty you have. So sort of the initial bet that you might make based on the fact that you think it's a mint coin is, it's going to be 50-50. And so that therefore I will bet $1 on heads because I want to play the game. And the thing with Bayesian statistics is, in conditions where all the probabilities are known, all frequentists are Bayesians. So if, for example, we're playing bridge, right? A frequentist and a Bayesian would use the same type of strategy of updating their probabilities and betting on what other people have in the bridge game. The issue comes in when you have uncertainties and basically uncertainties can be infinite. There's the type of uncertainty that I have in a bridge game of what other cards there are, and then there's the uncertainty of, well, if I win this bridge game, will the other two people I'm playing with kill me afterwards? Or, am I playing with a cute girl and she'll be receptive to my advances afterwards, and that type of thing. And those things, we can't assign clear probabilities from the physical. Like with cards, we can say there are 52 cards, so the probability of getting any one of them is 1 out of 52. But what's the probability that I get a date with a cute girl after I win at bridge? And this is both the strength and the weakness of the Bayesian approach, because basically what it's saying is you have to get those from somewhere. And if you're willing to make odds with it based on my knowledge and experience, I can sort of feed my subjective understanding of what my odds are into the mathematical formula. So the way to do it is imagine a roulette wheel that you can set for any odds of winning or losing, and then imagine your odds of winning a date with your bridge partner. If I feel as confident in making a $100 bet on that roulette wheel as I am getting a date, let's say 75%, and I'm like, yeah, both of those feel about the same, then I know that the prior that I should assign in this specific context is 75%. And there are other ways to get priors too, where you can look them up basically by saying, well, what's the probability of a uranium atom engaging in radioactive decay, and the other way is the same way the frequentists do, which is just gather a bunch of data and then determine what the actual distribution is based on that. And this is sort of the key part of this comic, is that for even the Bayesian statistics to kind of work, we have to know that the probability of the sun exploding is very, very small compared to the probability of getting 2 dice with 6s up.
So actually, going back to your bridge example, the Bayesian statistics, since it deals so much with conditional probabilities, it might, for example, to sort of extend the hypothetical a little bit, you could then consider the 2 outcomes of, if supposing you have the skill and the cards are relatively in your favor to win the game, and then you can ask what effect will that have on your likelihood of actually getting the date, versus if you lose the game, because you can always throw a game. Usually it's not very hard to lose in a game. So you could then look at the probability of getting that date under those 2 conditions. So looking at the conditional probability of getting the date under those 2 things, and so the to get some indication of, would it make sense to try really hard to win, or would it make sense to throw the game? I don't know much about bridge, and possibly it could be something like you have a full bladder. If you throw the game, you'll get out of there faster. Just to give you some motivation.
Yeah.
And presuming in this case, again, artificially, that winning the game makes you more likely to. But it seems that then what Bayesian statistics allows you to do is figure out, is it actually worth it? Because, of course, if I'm sorry, this is kind of a long question that I'm formulating, but because one thing that feeds into it is, it's not just that winning the game will make you 30% more likely, but you have to understand how likely is that actually, given the prior of how likely even getting that date is, sort of as the base likelihood. So that this way you can quantify, given these 2 things that you're not so certain about, if the result is winning the game will only give you a 1% chance anyhow, then you may very well not care and give preference to your bladder. Whereas if it gives you a fairly high probability, then so within that, it seems to me that's a way of quantifying how much you, in a sense, how much you know, in the sense of how much do you know you are likely to get the condition you want, in this case, the date.
Yeah, no, exactly. And that's basically the other part of this sort of mathematical thing is game theory, right? Where you have a payoff matrix of saying, for example, if I throw the game, the payoff is I get to use the bathroom, but the downside is my odds of getting the date with my bridge partner go down. Well, the other move is to try to win, and if I win, I get a date, but I have to hold my bladder, and then of course the other issue with that is how many utility points do I assign to each one of those things, right? Et cetera, et cetera. But that's basically it. Is that a good way to look at it is Bayesian statistics is about figuring out the odds for hands in a game that feed into your optimal betting strategy. And this actually ties into another sort of subtle point on the comic, that in some sense the Bayesian doesn't have to make any statistics at all, because if he's wrong about his bet, they'll both be dead momentarily.
Yeah, well, was it 7 minutes, 6 minutes,
Yes.
8 minutes, something in that range?
8.3 minutes.
Thank you. Yeah, I haven't gotten a lot of sleep lately. Yeah, so that's an interesting point, though. That looking at it in the upside versus the downside. Although they can be pushed. There's. Do you ever watch Lindy Beige, Lloyd from Lindy Beige?
I'm not familiar. Sorry.
He's a YouTuber. He does a lot of historical stuff. It's a good channel. I recommend it, by the way. Um, he talks about historical stuff and also Lindy Hop. But in some of his older material, there's some things he talked about the precautionary principle, which is where you work out that matrix in a very naive fashion. And it can be used about any number of things, but essentially, like, if I'm right versus if we're right, if we act versus if we don't act, and if it happens versus if it doesn't, producing a 2x2 matrix, where if we act and it happens, we're in the best case, we're much better off than if we didn't act. For there, and if it doesn't happen and we acted, we're not out very much. And although the best case is there, so sort of taking the two, or comparing the two, you don't lose much by acting, but you lose a lot by not acting.
Yeah. Sometimes it's called min-max, or basically you're trying to minimize the maximum loss that you're going to have no matter what happens, right?
Mm-hmm. Yeah, the problem with that is that in any sort of cataclysmic event, you can easily push this in a naive sense to you must therefore always act upon every threat, no matter how unlikely, as long as the devastation is sufficiently high. The problem, which of course, is that if you do this for many threats, the cumulative effect of acting on every extremely unlikely threat actually becomes, the cumulative cost of acting on every extremely improbable but very catastrophic threat becomes quite high.
Yeah, exactly. And which comes into the question of what's your expected outcome, right? So basically, the way that game theory or decision theory often works, at least in the mathematical way, we have slightly different heuristics, but it's you take your payoff matrix and you multiply it by the probability of each one occurring, right? Mm-hmm. So in this case, the sun going nova is 1 in a billion, and you multiply that against your cost function and say, like, it's going to cost you $1 billion equivalent to die that way. So if you multiply them together, the expected outcome is cost is $1. So in that sense, insurance would be worth it if it costs less than $1 to insure against this long-term effect. We run into different heuristics because we often deal with risks that we can choose how much we're exposed to them, and we're exposed to them many, many times, right? So like getting in a car is very different than the risk of species extinction from the sun exploding, because we can control how often we get into a car, and also because we're doing it many, many times, we want it to be as low as possible, because one fatal accident will kill you, but in your lifetime you might go like in a car 10,000 times or something like that.
Mm. Okay, so sort of drawing this to a close, because I think we've done a decent overview of what it is. One of the things that I see a lot in terms of problems with statistics is the belief that statistics are overstating this for effect, that statistics are essentially a magical incantation by which you can turn ignorance into knowledge. At its limits, you can. I'm pretty sure that if you were to describe to, especially people who are not mathematicians, a process whereby you take random numbers and then walk them through, a collection of statistical processes, you could probably fairly easily get them to believe that the outcome was, meaningful in some way, or the output rather of that was meaningful in some way. So it's very clear, though, if you know anything about the mathematics of ordinary probability, that frequentist statistics are not a means of turning ignorance into knowledge, because you don't. if you have a collection of things that you don't know how they behave, making assumptions about them and then adding a lot of these things together doesn't produce anything other than giving you a particularly clear view of what the assumptions you're making are. Essentially, it's a method of assigning numbers to the assumptions that you're making. So how about Bayesian statistics? Are Bayesian statistics a magical incantation which can turn ignorance into knowledge?
No, if anything, they're a way of combining your former knowledge through research or your intuitive understanding with new information that's coming in, right? So to use an example, if I was in a new house and totally had no idea who was coming down the stairs, Bayesian statistics would not help me at all determine who was coming down the stairs, right? It could be 1 out of 7 billion people because I've been magically transported into this house. But if I knew I was in your house or the White House, I would be able to say, okay, the footfalls are very slight, therefore it must be someone that weighs less than 100 pounds, and the only people in this house are whoever. And that way I can take my prior knowledge of knowing what house I'm in with the data that I'm getting from the footfalls down the stairs to come up with a inference that has specific mathematical probabilities associated with it, and say it's 75% chance it's person A, 25% it's chance it's person B, based on my prior knowledge and the sounds I'm hearing right now. That's sort of metaphorically what Bayesian statistics allows you to do.
Mm. And I guess sort of a final question. And this is just a perspective question, because they're two things that are equivalent to each other. But to take that, there's a 75% chance that it's one of the children. That one way of looking at things is to think of it as there's a 3 in 4 chance that I'm going to be right, and the other is that there's a 1 in 4 chance that I'm going to be wrong. And do you think do you have any commentary on choosing between these perspectives?
Yeah, so basically the way that Bayesian statistics works is it always sort of assumes that you have a known universe of possibilities, where if you're doing this calculation, it's one of the children or your wife, and that's sort of an assumption. You could always say it's one of the children, my wife, or someone I don't know about. And what that does is that just ends up scaling everything. And so basically what that means is that there's always a probability of length 1, right? It's either zero, it has to add up to 100%. And you can always slice those smaller and smaller, but you can't slice them so much that they become 0. And you can't expand them so much that they become greater than 100%. So in that sense, that would be determined by how you set up the problem, whether or not you're saying an unknown result is one of the possibilities, or I know for certain that it must be one of the children or my wife.
Okay. To some degree, the reason why I asked the question is because it seems to me that a lot of people use statistics in order to say, well, I'm not sure what to do here, so I might, hold off. But then if I do statistics, I can quantify things such that I now know how to act. And in some sense, that is the purpose of statistics. But at the same time, it seems to me that there's also that the very fact that there does become some sort of outcome which is favored over other outcomes can often cloud people's judgment as to how favored such an outcome can be. And is that something you've seen, by the way? Because it's something we talked about before the video, is that anchoring, how if you just be telling people numbers makes them think of them, even if they're unrelated, even if you explicitly have just made numbers up. that people somehow hearing numbers still makes people think of them and can anchor guesses to them and so on. But a related phenomenon, have you seen where if you can quantify, possible choices such that one of them is better than others, that people will tend to not think how good is the choice absolutely, given that they have one which is better than others?
That definitely does happen, especially when you're engaging in that type of modeling. The other issue, which if you actually do in the Bayesian approach, that helps, is you can see what people's prior beliefs are, right? So let's say that I'm going to use ice cream flavors because there's clearly the best choice of ice cream, which is mint chocolate chip. And the fact that that's in there would make me choose that as the ice cream to choose, regardless of what other statistics are. And so if I wanted to support that choice, I would say, well, clearly the way that we're going to do this is we're going to do a survey of people to determine what the best ice cream flavor is. But I know that it's almost certainly mint chocolate chip, and I'm actually 90% certain that it is, even before I do a survey. So I can put that as the prior in my Bayesian statistics, and then I survey people, and then that probability changes based on what people say, right? And so the first person is you, and you say, I don't like mint chocolate chip, I like chocolate, or whatever.
That was surprisingly accurate. I don't want to flip a coin between French vanilla and chocolate, but if it's a good chocolate, I'd go with the chocolate.
Well, yeah. And so I look at that and like, oh, well, here's one other person that said that mint chocolate chip wasn't. So clearly now mint chocolate chip has a 75% chance, just to pick a number out of the air. And then we pick another person and another person. And because your prior is explicit in Bayesian statistics, at least one level, it's open to analysis by others. So if I wasn't just surveying you, but sort of discussing the model with you, you would look at it and say, no, it's not 90% certain that mint chocolate chip ice cream is the best. Clearly chocolate is the best, or French vanilla. And then we'd have to have a discussion of how do we want to set our priors so that we get an outcome that really converges on the right solution based on the data. And that's sort of the other thing that you have to balance in Bayesian statistics is how tightly do you hold on to your priors. Because if I believe that mint chocolate chip was the best with 100% certainty, it doesn't matter how many other people disagreed with me. They're just wrong. And the other fascinating thing is
experimental error. That is,
yeah, exactly. It would be experimental error. They misspelled mint chocolate chip on the survey.
That is the problem, interestingly, and not to go down on a tangent, but it is one of the problems that actually comes up with all experimentation. And this came up with why falsificationism doesn't work. I don't know, for anyone who saw the video I did on falsificationism with Eve Kaninen, that the problem that Popper had, it's a great theory about falsificationism. The only problem is you can never tell whether or not anything's falsified because you can't know with certainty whether or not the experiment was in fact conducted properly and whether or not it really does invalidate this theory or possibly just some theory that's kind of similar to it. But even apart from that, there's no way to know for certain that the experiment was actually done correctly. It could always have been experimental error.
Yeah, and one of the things I love about Bayesian statistics is that if you take things that are like logical proofs, right, and you switch the logic of true and false into probabilities, then you end up with a Bayesian way of looking at it. And through Bayesian probability, you can actually model these things of what's your certainty, right? And this physics experiment was done by a bunch of monkeys. Therefore, the probability of it being right is 1 in 10,000. Or this one was done by Einstein, or pick your favorite experimentalist, by the CERN project. So it's 80% certain that they did it right. And then you can feed that into the certainty that you have on the theory to begin with and update accordingly. Of course, the problem is with this is that you can do this an infinite number of times. And so you end up basically having total uncertainty and are unable to make any updates if you're not certain of anything.
That is, yeah, it's the fundamental problem that all knowledge requires a leap of faith.
Yeah, exactly. And that's why everyone needs faith, unless they're going to literally take no action whatsoever or make no decisions. But then you need faith that that's the right thing to do, because you can't be certain of that either.
Yeah. For all you know, you're actually walking along someplace and need to jump left right now. That is the fundamental problem. At some point, this is something Eve likes to talk about, and this is really in danger of becoming a huge tangent. So be careful on that, because we're really at a good point to wrap up. But it's something Eve talks about, that all discursive knowledge ultimately rests on noetic knowledge, that is, direct knowledge, not obtained through any sort of discursive method, but rather simply knowledge by way of the mind coming in contact with reality. So it's sort of an interesting way to approach that through statistics, like you just described. Unless you start with some certainties, or in logic, unless you have some premises, that you have infinite uncertainty, or in logic, you just have no conclusions.
Yeah, exactly. And it's the same exact thing. And that's why like formal logic and Bayesian statistics is you make what those foundations or key parts of your argument are explicit. And then everything flows from there, and it allows you to communicate that with others and discuss them and modify them if they turn out to be incorrect. And you can also preserve them and give them to your descendants so that they don't have to guess at the priors, but can just look it up in the textbook instead. So.
Okay. Well, wrapping this up, just if people are interested in learning more about Bayesian statistics, where would you suggest, if going and taking college courses is not a convenient option for people, where would you suggest people look to learn more about Bayesian statistics?
There's actually a great book on this that I am looking up right now. So the absolute best reference on Bayesian statistics, and it goes on a few tangents as well, is Information Theory, Inference, and Learning Algorithms by David J.C. Mackay. So it's a bit of heavy reading. It's good to have at least some math before that. But if you want to learn Bayesian statistics and these types of things, and some applications to coding theory and information theory, and even touching on decision theory, this is the best book.
Cool. All right. Well, thank you very much, Andrew, for talking with me. It's been interesting talking about Bayesian statistics and learning some stuff.
My pleasure.
All right. And for anyone listening, until next time, may you hit everything you aim at.